Good morning, everybody. My name is Somya Sambit Mahapatra, and I work as a consultant in the Wolfram Technology Group. Today, I'll be presenting about responsive custom user interface design in the Wolfram language. We will start a discussion by looking into topics like delayed and stepped loading of an interface. We will look into the reasons for a dynamic being slow in certain cases. Then we will see how we can avoid unnecessary dynamics in order to improve the performance of an interface. We will look into various types of supported progress indicators that improve the aesthetics as well as give an indication that the interface is doing some sort of work in the background. We will look into a function called monitor that helps us to display the progress indicator and also its limitations. Then we will look into a monitor-like functionality that is suitable for usage with GUI applications. Finally, we will look into adding progress panes in a wide range of scenarios, and then we will look into a repository function called display with progress that encapsulates all these functionalities and improves the overall performance of a GUI application. So let us see how we can deal with slow interfaces. As we know, slow components in an interface lead to the degradation of the quality of the user experience. Here is an example of what we would call a slow interface. So in this example, we have a slider and there is a 3D plot that gets updated based on the position of the slider. Now when I try to change the position of the slider, we can notice that there is a significant delay in the response that is produced. This is what user would categorize as a very poorly designed application, and it tends to provide a very bad user experience. So let us see what are the general strategies to deal with a slow interface. Typically in any interface, there are two stages. The first one is called the loading stage, where different components of the interface are loaded. And then we have the operational stage, where the user actually interacts with the application to get some useful output. So in the loading stage, we can improve the performance by using a technique called delayed loading or stepped loading. And in the case of the operational stage, we can optimize by optimizing the kernel computations and avoiding unnecessary dynamics. Furthermore, there are certain calculations which cannot be optimized in any way. In those cases, we can employ the use of progress indicators to give an appearance as though the front end or the application is busy with something instead of giving a frozen-like appearance. So in order to manage the slow interfaces, we will be using delayed or step loading in the loading stage. We will try to optimize the kernel computation and avoid unnecessary dynamics in the operational stage. And after applying those two techniques, we would use progress indicators for the remaining slow components. All these techniques are going to be discussed in the subsequent slides. Let us see what we mean by delayed loading and how it is implemented. In functions like tab view, menu view, and pane selector, all the components are first evaluated and then the interface gets loaded. By using dynamic and image size, we can have the computations for each section done whenever the particular section is displayed. Let us see what we mean by this. In this example over here, we've got three sections of a tab view, tab 1, tab 2, and tab 3. And each section has got this pause statement of 2 seconds, essentially to simulate a long computation. And then there is some content. So let us see how these sections look. Notice we've got a tab view wrapped with all these sections. And when we try to evaluate this, it takes about 6 seconds to load all of them together. That's because each section would be taking 2 seconds to load. So after 6 seconds, we've got this interface over here. And we can navigate through each of these sections instantaneously. In order to compute the tab contents at the time when those are first clicked, we can use dynamic inside the tab view, and we can set image size to automatic. So here we have wrapped dynamic around each of these components, and we have set image size to automatic. And this takes about 2 seconds to appear. That's because the first section has the pause statement of 2 seconds, and since that is the first one that's going to be displayed, it took around 2 seconds. But now when I go to the second section, It takes another 2 seconds to render the content and then it displays. Similarly for the third section. But once they are loaded, we can move back and then we see that they are instantly, since they are already available in the memory. So the trade-off here is that, of course, we have to wait for 2 seconds for the first time we go into each of these tabs. So more information on how this technique works is provided in the documentation. In this example, we have used delayed loading with Pane Selector. First, we have created two panes. One pane contains a disk and another pane contains a square. Each of these panes have a pause statement of 2 seconds to simulate a long computation. Now, when they are displayed together inside a pane selector, this interface would take 4 seconds to load. So after 4 seconds, we get the interface where we have disks shown under the disk section. And when we move to the square section, we get this image of a square. However, this, as we noted, this interface took about 4 seconds to load. When dynamic and image size automatic are used, the interface loads in about 2 seconds. So we've wrapped dynamic around the individual content, we have wrapped dynamic around this disk, and we have wrapped dynamic around the square. And we have set image size to automatic. Now when we evaluate this, we get our interface ready in 2 seconds. So, and initially we have the disk selector. Now when we move to the square section, it takes about another 2 seconds for me to get the interface. But however, if I try to move again back to the square, it loads instantly. In this next example, we see how delayed loading is implemented into a practical example. Here we have used menu view and it shows GDP plot of various countries. In this first case, it takes really long time. And if you evaluate this, it would take about 40 to 50 seconds to load since all the country data is downloaded before menu view is rendered in the front end. So, but if we make some assumptions like the user won't be looking at all the plots simultaneously, we can optimize this by setting dynamic and image size to automatic so that it loads the plot for the countries which is currently selected. So in this second case, we have used dynamic around the date list plot, which is the actual content, and we have set the image size to automatic for the entire menu view. And in this case, if you try to move through a different country, it takes about a second to load the plot. Whereas in this case, since all the data is already downloaded, it almost updates instantly. The next technique that can be used to optimize an interface in the loading stage is called step loading. So in step loading, it is possible to reduce the loading time by loading only a part of the interface which the user can interact with. While the user is busy with the loaded part, the rest of the interface can be loaded in the background. So let us see how this is implemented. In this first technique, we use dynamic module. So here we have defined some styling options for frames, and then we've got these panes. We've got some content and then the frame options. So let's see how this looks. In pane 1 and pane 2, we've got our actual content, which is simply these numbers 1 and 2. Then in case of pane 3 and pane 4, we've got two types. We've got this pane 3 proxy, which has this content called a loading. Similarly for pane 4 proxy, and then we've got pane 3 real and pane 4 real, which has this pause statement of 4 seconds to simulate a long computation, and then the content. So let's see how pane 3 real looks. Pane 3 real would look something like the same as the content, but it takes about 4 seconds to load. So essentially, pane 3 has some long expensive computation and takes some time to load. So what we can do inside our dynamic module is we can set in initialization and then have synchronous initialization set to false. So here we have a dynamic module, and initially pane 3 and pane 4 will be set to the proxy content, which is loading, which is the string loading. And inside our pane selector, we would be having for the first two panes, we would be having the actual content. In the case of third and fourth, we would be having the dynamic content of pane 3 and pane 4. In our initialization, we set pane 3 to pane 3 real and then pane 4 to pane 4 real. And then we have the option synchronous initialization set to false. Setting synchronous initialization to false will allow the dynamic to display even when the initialization is not complete, and thus we can see the intermediate transitions between the variables. So we would see pane 3 showing loading initially, and then as soon as the actual content is loaded, we can see the actual content in pane 3. So right now we see in case of pane 4 we have the content as loading, and once that is loaded we see the actual content. In the second technique, instead of using asynchronous initialization, we can use asynchronous methods such as queues for stepped loading of an interface. In this example, similar to the previous one, we have again defined pane 3 and pane 4 to be of the proxy content, and here we have this symbol called inner all panes that has the all the different contents of the pane selector defined. So let's see how inner all panes look like. So we have pane 1 to be the actual content 1, pane 2 to be 2, pane 3 and pane 4 are initialized to the text loading. Then we've got this main pane selector where we have a button, and the button just has the label click to enter. And the point to be noted is that we have the method set to queued, and thus when we click on this button, it triggers the asynchronous initializations to take place. So when we click on enter, we go into our inner panes, and then we see the content which are not yet loaded, they actually show loading text, and once they are loaded they transition to the actual content. So basically the method queued is similar to synchronous initialization set to false. Let us take a moment to understand how interactivity works in case of preemptive links and main links. To give some context, the front end communicates with the kernel using two channels. The first one is called the main link and the other one is preemptive link. The main link is used for regular evaluations, and the preemptive link is used for high priority information transfer, which is usually the case with dynamic. So here we've got two sliders in the first two panes. So we've got the slider and the variable value placed in a row, and we are going to assign the pane code to pane 1 and pane 2. Pane 3 proxy and pane 4 proxy are going to be the loading content, and then pane 3 real and pane 4 real are going to have this long computation using pause statement. The interaction is going to be possible in pane 1 and pane 2 while pane 3 and pane 4 are loading. So here we have pane 3 and pane 4 still loading. If we go back to pane 1, we can still interact with the slider. This is because the slider uses the preemptive link. So essentially, any evaluation that uses the preemptive link is not affected with the asynchronous initializations. While a part of the interface is being loaded, any interactive component that uses the main link will not work. This is because the main link is used for loading the interface, and it remains blocked until the loading is complete. In this example here, we have a button that uses the method queued. So when I click on this button, it prints as expected. But if I make the main link busy with this pause statement for 20 seconds and I click on the button, it won't work. This is because the evaluation is blocked by this pause statement. If our purpose for using the main link is generally to do a time-consuming computation, we can still use the preemptive link, but with a larger dynamic evaluation timeout. So in this case, we have this button, and clicking on that button triggers this long evaluation and then prints this string. But we have used the dynamic evaluation timeout to be 20 seconds, and therefore the long computation generates the output. So after 8 seconds, we can see this string getting printed. However, while increasing the dynamic evaluation timeout, we should do it very cautiously as it may lead to some undesirable consequences. So when the preemptive link is busy, the front end will remain locked up and any interaction won't be possible with the interface. And the evaluations in the main link will also get paused. There are certain functions which are not even supported with the preemptive link, and queued links are only absolutely necessary in such cases, and system dialog input is one such function. There is another technique that can be used to improve the responsiveness of the interface. It is basically using a queued button in a separate kernel. I'm not going to go into the details of this technique, but I will give the general workflow. The example is provided in this slide and in the subsequent slides. So the general idea is that we use a button that runs on a separate kernel. We do the necessary computations in the new kernel, and then we bring the data back to the local kernel using the WSTP link. So below we have the example that uses this idea, and it explains how this is done. Let us now see how we can make the interface much more responsive in the operational stage. Before we go into the details of the different techniques involved in this section, let us try to understand when a dynamic is slow. So a dynamic update will be slow if the contents are actually slow to compute. In this example here, we have assigned x to 10, and then we have the statement dynamic, and inside it we have a pause of 1.5 seconds, and then we display the value of x square. When I evaluate this, it takes about 1.5 seconds to display the value of x square. And also when I change the value of x to something else, let's say 5, the update takes about 1.5 seconds to be reflected. So a more real example would be the nest expression that is used here. And so inside the nest, we've got a sign computation. And if we check out its timing, it comes to be around 3 seconds, 2 to 3 seconds. So let's assign k to 20, and then if we evaluate this statement that essentially computes the value of this statement, we get it to be 0.83, and the computation took around 3 seconds roughly. And let's try again by changing the value of k to something else, and the update should take another 3 seconds to take place. So there is no magic formula that would speed up the dynamic if the underlying kernel computation is expensive and long. But we can, however, optimize the kernel computation. We can try to avoid any unnecessary dynamics that would reduce the burden and make the interface more responsive and lighter. And we can gracefully deal with slow dynamics by using progress panes. Let us see how all these techniques work one by one. Computations in the Wolfram language can be optimized and speeded up by using various techniques like parallelization and compilation. And these techniques are discussed in the materials that are provided in these links. Avoiding unnecessary dynamics is a robust technique that can be used to make the interface fast and responsive in the operational stage. This works by avoiding any unnecessary dynamic updates to the static elements. For example, here in this code, we've got this dynamic wrapped around this list containing a pause statement that simulates a long computation. And then we've got this integer, and then we have the variable x1. Let's say x1 is assigned to 10. The dynamic update would take around 2 seconds to be reflected. So if I change the value of x1 to, let's say, 20, the update would be reflected after about 2 seconds. This can be avoided by wrapping dynamic only around the variable of interest, which in this example over here would be x2. So if x2 is equal to 50, the update almost takes place instantly. If I change the value of x2 to, let's say, 70, as you can see, the update was almost instant. This is because the dynamic is wrapped around only the variable and not the entire code, which has this pause statement and this integer 10. In this next example here, we see that the dynamic is wrapped around the this arrangement where we have a 3D plot and a sine plot. So when we evaluate this, it takes some time to compute, and then we get this output. Now if we change the range of this plot, it takes some time to calculate, because the entire 3D plot is recomputed every time this slider's position is changed. This is not ideal. So what we do is we instead wrap dynamic only around the sine plot for which the range has to be updated, and not the 3D plot. So in this case, we see the interaction with the slider is also much smoother, and the 3D plot is no longer getting recomputed. In this third example, we have this dynamic wrapped around an image size, a 3D plot. And what happens is in this case is that as I move my slider, even though I want to change my image size, but every time I move my slider, the entire 3D plot gets recomputed. To work around this, what we can do is we can put dynamic only around the image size and instead of the entire 3D plot. An intuitive way in which an interface can be made responsive is using the option continuous action. For slowly updating dynamic, we can disable the continuous action, and the update will happen only when the slider is released. For example, here we have this dynamic statement where we have a pause to simulate a lengthy computation, and then we display the value of x. When we move the slider, it takes about 0.3 seconds for the update to be reflected, and therefore it gives a bad user experience. Setting the option continuous action to false updates the value of the variable only when the slider is released. So when I move the slider, there is no update in the variable, and once I release it, the update takes place. This technique although comes with a price, that we can't see the variable being continuously updated. In this example, we manipulate the zoom level of the list plot 3D, and therefore we are able to continuously see the transitions. But if we set continuous action to false, as we have done here, we would notice that we can see the change only when the slider is released, and we are not able to see the intermediate transitions. Very similar to continuous action, we have the function called control active. When interacting with a control object, we can display something informative using the function control active. And the way it is done is that we wrap the function control active around the control variable, and the first argument to this control active function is the information that we would like to display when the controller that is tied to this variable is being interacted with. So let's evaluate this. When I move my slider, we get the text rendering, and once I release the slider, we can see that the latest value is shown. In this second example, we have this expensive dynamic where it is simulated by this pause statement. When we try to interact with the slider, it is a sluggish experience and it takes time to update. Using control active, we can show some information while we are interacting with the slider, and after the slider is released, it takes some more time and then updates. This way the interaction with the slider becomes much more smoother. In this third example, which is much more practical, we have a dynamic list contour plot which depends on the parameters a and b. So when I evaluate this, and whenever I move my slider for a and b, the entire list contour plot will get recomputed, and therefore this is going to be slow and computationally expensive, and therefore the update in the interface is sluggish. What we can do to improve the performance is we can use control active, and instead of showing any information, what we do here is we reduce the resolution of the contour plot by adjusting the intervals of the contours whenever the sliders are interacted with. And once the sliders are released, we can increase the resolution again back to normal. So let's see how this looks. So we've got the same plot, but this time when we interact with the slider, we get a lower resolution of the contours, and once we release the slider, it reverts back to the higher resolution. Another technique that we can employ for time-consuming updates is that instead of updating them continuously as a slider moves, we can use a button to trigger the update. So here is the same example that we saw in the previous slide that brings up a list contour plot, and the content gets updated as we move the sliders. However, this list contour plot is slow, so therefore we need to optimize it. And the way we do in this case is that we will have a button that triggers the update from the slider. So after evaluating this, we position the slider based on our choice, and then we click on the button update, and then this triggers the plot to be rendered. Similarly, again, we can change the positions of A and B and then click on update to get the new plot. In parts of interfaces where we have to switch within multiple sections, pane selectors can be more efficient in comparison to if. Let us try to understand this with this example. Here we have a setter bar to switch between two sections. There is the disk section and the rectangle section. And based on the selection, we use an if statement to show the content. And in the content, we have a couple of pause statements to simulate some long computation, and then we display our output. So let's see how this appears. So it would take around a couple of seconds, and we get the output. Now notice that if I change to rectangle, it takes a couple of seconds to switch. And similarly, if I go back to the disk section, it again takes a couple of seconds to show the output. This is because in the case of using if statement, every time I move to a particular section, it's going to evaluate this code. This is not the case in the for pane selector. In pane selector, similarly, we have the setter bar to decide which section we want to use, and then we use pane selector to point to the particular content. And in the output, it takes about 4 seconds to display, and then when I move to the rectangle section, it shows the output instantly. So this is the advantage when using pane selector. We can also improve the responsiveness of an interface whenever an expensive kernel computation is involved by pre-computing the values beforehand and storing them in a table. Accessing the elements from the table is going to be much less computationally expensive than calculating them on the fly. For example, here we have this function myFun, and it has got this long computation simulated by this pause statement, and then it returns the value of n square. When I evaluate this using this interface having a slider and calculate the value of myFun, interacting with the slider is going to be sluggish because of this long computation. What we can do is we can instead compute the values and store them in a table with the variable myFun values, and it takes about 10 seconds to get evaluated for all these values. And after it is calculated, we can fetch the values from this table based on the part function, and in this case it is going to be much more responsive. For a time-consuming dynamic update, asynchronous updating is preferred over synchronous updating. This is because in case of synchronous updating, the front end remains locked up until the evaluation is completed. For example, here we have this dynamic statement with pause 5 and then the value 10 is displayed. When we evaluate this, the front end gets locked up until the value 10 is displayed. To work around this, we can convert this to an asynchronous updating by setting asynchronous updating to false. So during this case, I can still interact with my front end, and after this evaluation is complete, the value is displayed on this side. In the second example here, we see that the front end remains unresponsive after the slider is released until the plot is displayed. So I move my slider and I release the slider. The front end remains locked up until the plot gets updated completely. To work around this, what we can do is we can set the synchronous updating to false inside the dynamic. And now whenever I move my slider, I can still interact with the front end while the calculation is going on the background. An even better approach is to show a progress indicator while the update is taking place. And this is the topic that we are going to discuss in the next section. Let us now discuss about progress panes and see how they can be used in interfaces to give an indication that something is going on in the background. So while we have learned various techniques for making an interface more responsive, there are certain slow updates that are absolutely unavoidable. For example, in this case, we have the slider, which would take at least one more second to show the update despite the slider being smooth. What we can do is we can use a progress pane to show the update in the progress while the result is not yet displayed. So we have this function called progress indicator that has different styles, as we can see here, and this can be coupled into an interface by using the function called monitor. So here we have a pause statement, and then we are going to display the value 10, and then we give the type of progress indicator that we would like to display. So what happens during the first 5 seconds is that we get our progress indicator. So this shows that the interface is busy calculating something, and after that 5 seconds we get our output. So for more than 8 seconds, it would be a good idea to show the extent of the progress. So here is a dynamic wrapper that calculates the progress based on this calculation. So value of I increments in steps of 1,000th of a 2. And we see the increment here. However, the extent of progress accurately is not always possible to be calculated, and it requires the knowledge of the internal state of computation. For example, in case of integrate, we might not know how much long the integration is going to take place. In such cases, we can use the indeterminate progress indicator. So we have seen that the monitor function can be used for showing progress indicators while doing some computations. However, the limitation of monitor is that it can be used only with the notebook environment. This is the example that we saw in the previous slide, and it displays the progress indicator for 5 seconds and then shows the value 10. Monitor does not usually go well with GUIs, specifically in case of this dynamic update that is coupled with the monitor function. If we evaluate this, it waits for a couple of seconds and then directly shows the value instead of showing the progress indicator. This is because monitor works by creating a new cell, and thus we cannot use monitor in a GUI update only to a particular component without disrupting other components. In this case over here, we have a list in which the monitor function is an element inside the list. So when we evaluate this, we see that the progress indicator appeared in one cell, and then it created a new cell to generate the output. So to work around this, we can create a monitor-like functionality that is suitable for usage with GUIs and other dynamic or dynamic modules. Let us discuss a monitor-like functionality that is suitable for usage with GUI applications. It is created using this dynamic module where we have this local variable loaded, which is initially set to false. In the content area, we have an if statement that checks the status of the loaded variable. If the loaded variable is set to false, it shows a progress indicator, and once it is triggered to true, it shows the actual content. Our main computation code goes into the initialization part, and once the initialization gets completed, we change the loaded variable to true, and finally we set the option synchronous initialization to false. So the key takeaways are: the dynamic module should be initialized with asynchronous initialization. The main time-consuming code is sent to the initialization part. The flag loaded is initially set to false, and then when the main computation is over, it is set to true. And during this time, we can show a progress indicator when the loaded remains false, and once it turns to true, the final object can be shown. This entire idiom is encapsulated into the super function called display with progress, and the usage for this function is also illustrated in the following slides. Let us take a look at few examples for the monitor-like functionality for GUIs. In this first example, we are going to use the monitor-like functionality for a long computation time. So we have this object where we have a long computation of 5 seconds, and then we display the text ready. We plug this into the idiom that we saw earlier that uses the dynamic module with the synchronous initialization set to false. So when we evaluate this, we see our progress indicator for about 5 seconds, and then it shows the text ready. So our main code has been plugged into the initialization part of the dynamic module, and the synchronous initialization is set to false for this to work. In the second example, we are going to use it with a long rendering time. So we have this graphic that takes a long time for being rendered. So it takes around 3 to 4 seconds for the graphic to appear. And then we have this progress pane that shows the text loading at the center. And in our function, in our dynamic module, we have set the flag to false. And in our content area, we check the flag status and then display either the progress pane or the graphic. In our initialization, we set the loading to true. So when we evaluate this, initially during the loading stage, we get the loading text, and once the loading is completed, we move to our graphics. This entire functionality can be used directly with the display with progress functionality that we discussed earlier, and it can be used in this way. So the first argument can be the rendering computation, and then the progress pane can be given as the second argument. So when we evaluate this, we get the progress pane for first few seconds, and once the graphics get rendered, it switches to the graphics section. The same can be used with dynamic objects, and the setup is pretty much similar, where we have the dynamic module and then the content area. In our initialization, we plug in the actual computation, and then we change the status of the flag to true once the computation is completed. So it shows the progress indicator, and once it is done, it switches to the text ready. And this can be done with the display with progress as well, using this setup. The discussed idiom can be used additionally for displaying progress indicators in cases where we have time-consuming dynamic modules for updates using control objects like buttons or checkboxes, and also for updates with continuous action or control active. And note that unlike monitor, display with progress can show progress indicator for one component in the interface without disturbing the others. So this is an example that we had seen earlier, where the monitor function is a part of the list. In this case, the progress indicator appears first, and then it creates an entirely new cell to display the content. Whereas if this is created using the display with progress function, the progress indicator appears in place of the list. So this does not create any additional new cell, and it does not disturb any other components in an interface. Here is another example of using display with progress in the loading stage. So we have modified this example from one of the earlier slides, where we have different sections in the tab view, and we applied display with progress to each of the tabs. So as we move through different tabs, we notice it is showing this progress indicator, and once the content is loaded, it shows the actual content. So to summarize, we started with discussing about how we can manage slow interfaces in the loading stage. We discussed about delayed loading, where we load the components on as needed basis, and then we saw stepped loading, where we load a part of the interface, and while the user is interacting with that part, we load the rest of the interface in the background. We saw that a dynamic update would be slow if the underlying computation is expensive, We discussed how an interface can be speeded up by using dynamic only in places where it is absolutely required. Then we saw various methods for avoiding unnecessary dynamics. Some of the techniques were avoiding evaluation with Pane Selector and using pre-computed values. We saw various different types of progress indicators that are supported in the Wolfram language. Some different styles were necklace, ellipsis, indeterminate. We saw that monitor is not suitable for showing progress indicator in a GUI application. Then we discussed a general idiom for using dynamic or dynamic module for showing progress indicator in an interface. Then we saw how the idiom can be used to display progress indicator in wide range of scenarios, like displaying a static object, a dynamic object, or while rendering something. And we also saw the use of resource function, display with progress. That concludes this presentation, and I'll be happy to take any questions. Thank you.